Hello and welcome. We will continue with our discussion of multivariable systems. So last time we looked at interaction metrics. Steady state interaction metrics. Namely the Netherlinsky index and the relative gain array. And we saw that if the Netherlinsky index is less than 0, those pairings should be avoided. And relative gain array told us that pairings with lambda ij less than 0 must be avoided, and we should prefer pairings with lambda ij close to 1. So once we have decided on a pairing, there's another thing that helps us decide pairings, and that's the Speedo response dynamics. And so let us say I've got a variable that to control, that's y1, and I've got u1 and u2, and I can control y1 using u1 and I can control y1 using u2. What you actually look for is prioritize the variables, and there's also y2 that you need to control. And what you would find is you want to, let's say the prioritization is y1 is more important, y2 is not, so y1 is more important, y2 is less important. So I want tight control of y1. So what you would do is, okay, y1 needs to be tightly controlled. So between u1 and u2, which one has large and fast effect on y1? So you should prefer large gains and fast dynamics. So just by looking at the transfer functions, how fast, what are the time constants, what's the dead time, one can come up with pairings, and then you can confirm, okay, the Netherlinsky index is acceptable, the relative gain is also acceptable. So these can be used as confirmatory tools. But as far as pairing goes, one can also use common sense and prefer pairing, making those pairs that have a large open loop gain and fast dynamics. So that's just applying common sense. Applying common sense. Okay, so once the pairing is done, now comes the question of designing the controller. And like I said, the decentralized control system is the most common way of doing it, simplest and probably the best. Decentralized control. And what do we do in decentralized control? And I'll just give you an example for a 2x2 system. Each output has its own controller that works based only on the error in its controlled variable. So we've got this 2x2 system, and a decentralized control system would be y1 being controlled using its own controller, and y2 being controlled using its own controller, That's a decentralized control system. So in this control system, what we have is, and this is E1, this is E2, and what we have is, and this is U1, and this is U2, and what we have is U1 is equal to GC1 E1, and U2 is equal to GC2 E2, and you can see the dependence. U1 moves based purely on E1, U2 moves based purely on E2. That is why it is called decentralized control. You mind your own business, I'll mind my own business. So the Y1 controller minds its own business and does not bother about what the other guy is doing, what the neighbor is doing. And I think that's the best way of living life, because if you start poking your nose in your neighbor's affairs, you know, things can go south very quickly. Okay, so U1 varies based purely on E1, U2 varies based purely on E2, and even though we know that when you change U1 it affects Y2 and hence E2, and when you change U2 it affects E1 and hence it affects Y1 and hence E1. Okay, so the interaction between the two is compensated by each of the loops using its feedback action, and that's why it's called decentralized control, because each controller does its own job and doesn't bother what the other guy is doing. It's decentralized. Okay, uh, and we saw last time that this can be written as U is equal to maybe I should, this can be written as which is U is equal to the controller matrix times E, and this controller matrix is diagonal, and this diagonal structure for the controller matrix is implying decentralized action, meaning each one does its own job and doesn't bother about what the other guy is doing. And you can extend it to an n by n system. And we also saw last time that there is this figure of 8 interaction which is in addition to the usual loop feedback. So there is an additional loop, and I'll just draw that additional loop. So there is this additional loop, and this is due to G21 and G12 non-zero. If any one of these is 0, this interaction, this loop will be broken. If either G21 or G12 is 0, the figure of 8 loop interaction won't be there. And so this is an additional feedback loop, and this additional feedback loop requires detuning. I wouldn't say require, that comes later, because there's an additional feedback loop. It will destabilize the system, and because the system is destabilized because of multivariable interaction, the multivariable system tuning will have to be detuned. So you require detuning. So you require detuning from the usual CISO settings, from usual CISO settings. Okay, decentralized. Okay, so now the question comes, how do we decentralize? How do we detune? What is a systematic way of detuning? In order to obtain that systematic way, there's the common sense approach. And what's the common sense approach? Common sense approach is as follows. What you do is, you've got your system. I'm sorry, I'm having to draw it again and again and again. So so in this case, the common sense approach is, we want to tune loop 1 and loop 2. So this is loop 1 and this is loop 2, and we want to tune these two loops. The common sense approach is, between y1 and y2, usually what will happen is, tight control of one of the two would be more important than the other. So without loss of generality, let us just say y1, tight control of y1 is more important than tight control of y2. Alternatively, usually the dynamics of loop 1, the dynamics of one of the loops may be much faster than the dynamics of the other loop. And again, without loss of generality, we may say that, let us just say that loop 1 is much faster than loop 2. Either case, what we then say is, okay, I will tune loop 1 first, and I will tune it to its CISO settings. So tune more important loop, more important or faster loop, whichever, more important loop to its CISO settings, to its CISO settings. Other loop is off. Other loop on manual. Then what you do is, tune Next important loop, with previously tuned loop on auto. On auto. And keep doing this and keep repeating this till all loops are tuned. So this is the way to tune. And in this very simple y1 y2 example, you tune loop 1 with loop 2 on automatic on manual, and loop 1 is therefore tuned to get you get some very tight tuning such as Ziegler-Nichols or any other setting, or closed loop damping coefficient of 0.5 kind of tuning, or a maximum closed loop log modulus of 2 dB for loop 1. Then what you do is, with loop 1 already tuned and on, you tune loop 2, and again you do the same thing, obtain KU PU and apply some tuning rule, or obtain the gain such that you get so much overshoot or so much decay ratio and so on and so forth. Okay, but now because loop 1 is on automatic, the figure of 8 interaction is operative when you're tuning the loop 2. On the other hand, when loop 1 was being tuned, because loop 2 was on manual, the figure of 8 interaction was not there. So in this way you get very tight tuning for loop 1, and all the detuning ends up in loop 2. So thus, if y1 is more important to control than y2, you get very tight control of y1, and you get loose control of control of y2, and in this way all the detuning gets taken into y2. All detuning which is necessary, all detuning necessary due to multivariable interaction gets taken in loop 2. So this is the very simple in loop 2, which is less important. Now somebody will say, oh well, let us say both y1 and y2 are equally important, or alternatively let us say the dynamics of both y1 and y2 are on a similar time scale and also equally important. Then what do we do? Then we need to distribute the detuning into both loops. Loop 1 also needs to be detuned, loop 2 also be detuned, but we don't want to detune loop 1 too much, and we don't want to detune loop 2 too much. The detuning has to be balanced between the two loops. Okay, so when both, or let's just say balanced detuning, like all this we want to detune in a balanced manner. So balanced detuning. How do we do balanced detuning? Well, there is what is called the biggest log modulus tuning, BLT, which is proposed by Lieben, which I think is quite intuitive and to the point and doesn't beat around the bush too much. And I'll just propose this and describe what it is to you and then leave it. So what do we do in BLT detuning of multivariable systems? So what you do is obtain individual loop tuning for all loops. And when I say individual, what I mean is when you're tuning a particular loop, all other loops are on manual for all loops. Okay. So therefore you've got tau I Zn. You also got Kc, for example Ziegler-Nichols, and let us just say we are doing PI controllers, no derivative action. Okay. So obtain individual loop tuning for all loops, tau I Zn, Kc Zn. And now what we want to do is detune each of these loops by a factor f. So now what I want is f, which is a detuning factor which is greater than 1, which is a detuning factor and how do we detune it? The implemented tuning is going to be Kc that you're going to implement in a loop is going to be Kc Zn for that loop divided by f, and tau I for that loop is going to be f times tau I Zn. And if there are, and I'll just put a subscript I here. I'll just put a subscript I here. So all the loops I going from 1 to n, if there are n loops, if there are n loops, that's what we do. Now the question is, what should f be? What should this detuning factor be? And it is here that we do an analogy with CISO systems. The maximum closed loop log modulus so the maximum closed loop log modulus of 2 dB for a CISO systems, analogy with CISO systems. What is the analogy? In a CISO system, hang on. Let me develop the analogy. So CISO and multivariable. In a CISO system, what's the closed loop characteristic equation? The closed loop characteristic equation is 1 plus GPGC is equal to 0. That's the closed loop characteristic equation. Its multivariable counterpart is determinant of I plus GP matrix times GC matrix is equal to 0. Okay. How do I define when I take the log modulus? I define a transfer function. What is that transfer function whose log modulus is taken? That transfer function is, actually that transfer function is G closed loop is equal to GPGC divided by 1 plus GPGC. Now if you look at this transfer function, this is actually equivalent to, in the CISO domain, the closed loop characteristic equation in the denominator and minus 1 plus the closed loop characteristic equation in the numerator. So let me define so let's define W is equal to minus 1 plus determinant of I plus GP GC, and then by analogy I will define the multivariable counterpart of G whose log modulus I am going to take as W, which is minus 1 plus the closed loop characteristic equation divided by 1 plus W, which is the closed loop characteristic equation. Note that this is equivalent to closed loop characteristic equation multivariable minus 1 plus divided by closed loop characteristic equation multivariable. So that's what we have, W over 1 plus W. So now we say that, okay, let me define G as this guy for multivariable system, and then my log modulus is going to be 20 log on base 10 of the absolute value of the complex number W over 1 plus W. And then what I do is I adjust F. By the way, the procedure then is you assume a detuning factor F. Each of the loops Kc and tau I are known, and now we're going to detune from that Kc and tau I. So you assume F, a detuning factor F, which is greater than 1. Obtain L over a range of frequencies, relevant frequencies, obtain L over relevant frequency range, and then also obtain L max, maximum log modulus, and I will put a CL there because it's closed loop. Okay, and then we say this LCL max, is this equal to, if there are n loops, 2 times n dB, because each of the loops can contribute 2 dB to the hump. Okay, so if there are n loops, you'll get 2 n dB. Is this equal to 2 times n dB where there are n loops? If yes, then you have detuned successfully. If not, reassume f. Let us say LCL max is greater than 2 dB. Let us say it is 6 dB. Sorry, let's say there are 2 loops. So you want LCL max to be 4 dB, and let's say your LCL max turns out to be 8 dB. Then what do? You increase the detuning, and that 8 dB will then go down, and you keep on increasing f until that 8 dB goes down to 4 dB for a 2 by 2 system. And if yes, exit. So this is the procedure, and then the implemented tuning is kcZn by f and f times tau I Zn. So that's sort of the procedure for balanced detuning. So in a sense, we have detuned each of the loops by the same factor f from its individual Ziegler-Nichols setting in this example, in the way that it has been proposed. So all the loops are equally detuned. It is not that the detuning has been taken in only one loop and things like that. Yeah, so all the loops have been detuned in a balanced manner. Of course, the tuning that you get with this procedure, usually you require to confirm the closed loop performance using simulations, and one must treat the tuning that you obtain just like in Ziegler-Nichols. Tuning is also indicative. Sometimes it can perform very poorly even for CISO systems, and uh, the tuning rules that you apply, they get you an initial ballpark. So this procedure will also get you an initial ballpark tuning for each of the loops. You may have to fine tune the tuning a bit more. Okay, so this is the balanced detuning procedure for uh, multivariable systems. So now we know how to detune or how to tune a decentralized multivariable control system. Okay, now sometimes, when I repeat sometimes, when set point tracking is important, which is not the case in chemical systems, but for example robots and aeroplanes and missiles, you're tracking a set point. When set point tracking is the primary purpose of the control system, in those cases often decouplers, dynamic decouplers are used. And what do I mean by dynamic decouplers? One of the simplest ways is to apply feed forward ideas. So we'll just take an example for a 2 by 2 system, and now this U1 signal from Y1 controller. This signal is coming from the controller for Y1. And the U2 signal is coming from Y2 controller. We have a decentralized control system, and there is a Y1 controller and a Y2 controller. Okay. Now, I say if Y1 controller is going to change U1 by a certain amount, then I know that Y2 is going to change by G21 times whatever is the change in U1, and then what I can try and do is put a feed forward controller here, and what should be in this block from our analysis of feed forward systems, you would know. Maybe I should draw it a bit differently so that it turns out to be a bit more clean. What should go into this transfer function so that when it is its output अरे यार कैसे डालें इसको okay, so maybe I'll just do it this way. What should I put in here? What should I put in here so that when U1 is changed by the Y1 controller, counter action is taken by U2 so that this is exactly the opposite of this, and when you add these two signals up, the deviation in Y2 is actually 0. And from our knowledge of feed forward control, we know that what should go in here is actually minus G21 by G22. I say, well, so this is one-way decoupling. So now U1 changes, Y1 changes, but Y2 does not change. I can also apply two-way decoupling and say that what should I put in here? What should I put in here so that when the Y2 controller is going to change U2, a counter effect is taken onto U1 so that Y1 does not deviate from its set point. So the deviation in Y1 is 0. And from our knowledge of feed forward control, we know that this guy should be, arey yaar, this is getting slightly messy, but it's getting there, G11. And this is the change that I should be making on this guy. Everything is plus here. So actually, if you look, This is my process. Hang on. This is my process, which I cannot change. It is what it is. But then this is a calculation block that I have added. These are calculation blocks that have been added. Calculation blocks that have been added. And with these calculation blocks in place, assuming that the cancellation is perfect, you will find out that if you obtain the transfer function and let's call this signal u star, so let's call this signal u star, u1 star, and this signal u2 star. So what you'll find is that as far as the controllers are concerned, the y1 controller and the y2 controller, u1 star affects only y1. You see, u1 affects both y1 and y2, but because of the calculation block that I have implemented, u1 star affects only y1, no effect on y2. u2 star affects only y2, no effect on y1. Okay, so if you, for example, let us say I wish to obtain the relationship of y2 with respect to u1 star. Let us just say I want to do that, y2 u1 star relationship. So y2 is going to be so y2 is going to be g21 times u1 star minus g21 by g22 into g22 u1 star, which is actually, if you want to see it strictly, minus and of course in reality we will only have a model of this guy. We will never have, but if we have a perfect model, this term in the square brackets actually goes to 0. If we have an imperfect model, then this term in the square brackets is approximately equal to 0. There will be some dynamic imprint that you have because of plant model mismatch, but if you have a perfect model, it will actually goes to 0. Similarly, you will see that okay, the other thing that let us look at what will be the impact on y2 of u1 star. So if you so if u1 star goes up, what happens to y1? So let's look at that. So if u1 star goes up, y1 will actually go to g11 u1 star, but this change in u1 star will cause a change in u2, which is actually minus g21 by g22, and this will cause an additional effect g12 on y1 because of u1 star. So if you look at the relationship of y1, it's actually g11 minus g21 by g22 g12 times u1 star plus g12 minus g12 by g11 times g11. And just to be really spot on, we'll say that this is actually a model times u2 star, and this approximately is 0. Notice that with the decoupler in there, when the controller changes u1 star, if the decoupler was not there, the effect on y1 would have been g11. But because the decoupler is there, there is the g11 effect, and there is the additional effect because of the change in made in u2. Similarly, you will find that y2 is equal to g21 minus g21 model divided by g22 model times g22 times u1 star plus g22 अरे यार oh minus oh well so there's the g22 effect, and then there's the g21 divided by multiplied by g12 by g11. Yeah, and again you see this is approximately equal to 0 if the model is good, and this is the additional effect because of the decoupler that has been put in place. So with the decoupler put in place, the y1 controller sees a different dynamic characteristic, different dynamics for y1, and the y2 controller sees a different dynamics for y2 with respect to u2 star. So the u1 star y1 dynamics and u2 star y2 dynamics are different from u1 y1 and u2 y2. Yeah. So but the beauty of the system is, if you look at it in matrix form, what you then get is, and I think maybe I should just put it in here, what you then get is that y1 y2, and if we assume that those cross diagonal terms are actually perfect, and plant model mismatch is perfect, there is no plant model mismatch, then what you get is g11 star g22 star, this guy is 0, this guy is 0, multiplied by u1 star times u2 star, and I'm calling this guy g11 star, and we are calling this guy g22 star. Yeah, so now you get a nearly diagonal system. Even if there's some plant model mismatch, you get a nearly diagonal system. Yeah. So dynamic decoupling results in a nearly diagonal system, and now you can tune y1 u1 star using CISO, pretending as if the other loop doesn't exist. Then you can also tune y2 u2 star pretending as if the other loop doesn't exist. But please note that should the plant model mismatch increase, performance will degrade very quickly. That's the disadvantage of all these model based techniques. The decoupling is model based. If plant model mismatch is not so good, then you end up actually second guessing yourself, you know. So it's like you start thinking on the other person's behalf what he's going to do, and anticipating what he's going to do, he or she is going to do, you start countering those measures. Now, as long as your anticipation is correct, things would be fine. But if the other guy does not behave the way you expect him to behave, you're going to end up in a mess. That is why they say it is best to, uh, just think on your own behalf and be honest, because that relieves you of the burden of what the other guy is doing. So decentralized systems are actually very robust. Okay, but in mechanical systems, aerospace systems, decoupling is often used because now you get very tight control of y1 and very tight control of y2, because the decoupler has given you essentially a diagonal process system, a system with a diagonal process structure. So now what I'm trying to say is, you see, the process in the blue, that has a non-diagonal structure, but this process this is diagonal. Diagonal meaning decoupled. Actually, it's nearly diagonal, not exactly diagonal because of plant model mismatch. Okay. With this, I think I'll end this lecture. What we have seen in this lecture, we have looked at uh, decentralized controller tuning, in particular we looked at sequential, tune the most important thing first, followed by the next guy, and followed by the next guy, and so forth. And we also looked at balanced detuning. And then we also looked at dynamic decoupling, which is of much relevance in mechanical and aerospace systems. Okay, so that's that. Thank you for your kind attention. Hope to see you next time. Thank you and goodbye.